So hello everyone, welcome to the last session. And today we have our organizer and speaker, Professor Nabil Iqbal. He is a professor in Durham University. And everyone probably knows him by now, apart from his excellent research career.
নাবিলকে ভাই বলে ফেললাম।
Okay. So apart from his excellent research career, he holds schools and does a lot for the developing countries. And his papers are super diverse. If anyone has a look at it, they're super diverse, and he is an inspiration, I think, to all of us here. So over to Nabil.
Okay. Thank you very much, Rakin, for that wonderful and embarrassing introduction. It's very kind of you. Okay, so let's get started. I'll say this is the last scientific lecture of our little school. And I'm going to take the time to talk about quantum field theory for phase transitions. So the title is Quantum Field Theory for Phase Transitions of Magnets and Boiling Water. And the basic idea is that, you see, in these lectures so far, we have mostly discussed quantum field theory sort of as applied to particle physics. You know, there was stuff about the standard model and so on. But it turns out that the ideas of quantum field theory are really useful for understanding many, many different kinds of things. And today I'm going to tell you how to use quantum field theory to understand phase transitions involving magnets, which people have probably are already a little bit familiar with. And I'll show that there are important things happening with magnets that the right tool to discuss this is quantum field theory. And the real reason why this happens is because quantum field theory captures the idea of fluctuations and locality, and those things are present in many, many, many systems. Okay, so the goal of today is to connect quantum field theory. Here we go, is to connect quantum field theory as we have studied it to problems in statistical mechanics. So let me begin by telling you about some very basic system in statistical mechanics. Okay. So suppose we want to understand magnets. Magnets are cool. We all have them on our fridge, and we might want to understand magnets. Let's begin thinking of what a magnet is. So the simplest idealization of a magnet is something like the following. Imagine taking some sort of chunk of metal, okay? So the chunk of metal has atoms that are arranged on some lattice like this, say. And now on each site of the lattice, let's place a spin, okay? So we're doing classical statistical mechanics, so I should explain to you exactly what I mean by spin, okay? So for this part of the lecture, you imagine you have a chunk of metal, so you have a lattice with a spin on each side of the lattice. And when I say spin, I imagine that you take a vector n, okay, living on this site. So here, this I runs over the sites, okay? And you have a vector, a 3-vector living on each site. But however, let me normalize the 3 vectors so it has norm 1. So I'm going to normalize it so that for each of them it has norm 1. And what that means is that actually this vector really lives on the surface of a sphere. Okay, in fancy language, we'd say it lives in S2. So you should imagine that each of these vectors lives on the surface of a sphere. Okay, its norm is 1, but it can point around in whatever angle it likes in 3 dimensions. And so the degree of freedom is an angle, not one angle really, rather like 2 angles on each lattice site. Okay. So we are now doing classical statistical mechanics. So we're going to use the tools of quantum field theory, but it's not really quantum. We're going to do classical statistical mechanics. And what that means is I need to give a Hamiltonian, a classical Hamiltonian for this spin system. So what is the Hamiltonian? The Hamiltonian is something which is valued on all of the spins. All right. And we're going to take it to be the following. It's minus J. J is just a number, coupling. Oops. Okay. So let me explain what this terminology means. So this thing here, this ij in angle brackets, this thing here means sum over the links. Okay. In other words, on this lattice, we have links between lattice sites. So for example, here's a link, 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 here's a link. This nij means that we sum over each of these links. Okay. And now when you sum over a link, which connects site I to site j, that's what this ij means, you take the dot product of this vector with this vector. That's what this ni.nj means. And then you add that up, summed over all of the links of the lattice, and you get this Hamiltonian here. This measures the energy of that spin configuration. Okay. So this model that I'm telling you about is called the Heisenberg model. Okay. Heisenberg did many things, of which one is this simple model of magnetization. All right. So I claim this is almost the simplest model of a magnet. It captures some basic ideas of magnets, but not everything. But it captures enough to see the interesting physics that we want. And in fact, it's simple, but it's still not simple enough. We're going to have an even simpler one in about 5 minutes. But I'm presenting you this one first. Okay, I see there's a question. Let me allow, so I'm allowing you to talk now in this question. Is there still interest in asking a question? This may have been up for a while. Maybe not. Okay.
For now, I have.
Okay, cool. Okay, I'm gonna keep going. All right. So, if there are any questions, please write them in the chat, and I'll do my best to answer. Okay. So, this is a very simple model of a magnet. Okay. Are there any questions at this point? Any other questions as to how this works? Okay. Now, let's now understand the physics of this magnet. So the way this works is we're doing again statistical mechanics. So we should construct a partition function. And now we've done some of these things already in this quantum field theory class. You can see that it's kind of the same idea as in statistical mechanics, right? So in the path integrals part, we talked about creating a partition function, which involved integrating over some, degrees of freedom, doing a path integral. Here we integrate over n, the vector, on each site of the lattice, and we compute the partition function as e to the minus beta of h. Okay, where h is the Hamiltonian. You can see this looks kind of like an action, right? In the quantum field theory class, we had path integral over e to the is. It's kind of the same idea, except it's e to the minus beta h. It's Wick rotated. Okay. Now let us understand the physics of this simple model. So first, beta, as you know, is 1 over the temperature. So you can think about this as really saying 1 over T. That's what's happening here. Now, what happens to the system at low temperatures? At low T, the system will typically want to, reduce its energy, right? At low temperatures, everything wants to sit in as low an energy state as possible. So how do we lower the energy? The way we lower the energy is, let me just remind you what the Hamiltonian is. We scrolled past it. It's something like minus si.sj on all the links. Now, what is a dot product? A dot product is really basically the angle, right? So what this is saying is sum over cosine of theta ij, where theta ij is the angle between two neighboring spins. Okay, this angle. Now, what this says is we want to lower the energy, but there's a minus sign here, which means we want to make the angle as big, the cosine of the angle as big as possible. Cosine of 0 is 1, and that's as big as it gets. So what that means is we lower the energy by making all the thetas ij parallel. Okay. Which means that we want all the spins to line up. That's what it means, right? If all of the spins are parallel, then all of these angles are 0. So if we have all of the spins aligned, then all the spins point in the same direction. This happens at low temperatures, and this is exactly what we call a ferromagnet, right? You've probably encountered this in your elementary physics classes. The definition of a ferromagnet is that all the spins that make up the system are all aligned. Okay? So this again happens at low temperatures. Okay? In physics, you should always study two different limits. Take a parameter, make it as small as possible, which we just did. We made t 0. Now make t as big as possible. So we can ask what happens at high temperatures. At high temperatures, everything will fluctuate like crazy, right? That's what the meaning of high temperature. In other words, system wants to maximize the entropy. This is just normal conventional entropy. It is not the fancy entanglement entropy that we talked about yesterday. It's just normal thermodynamic entropy. And that is maximized if all the spins are basically just doing something random, you know? So if all the spins are fluctuating wildly, if there's no order or anything like that in the system, then this maximizes the entropy. Notice that the spins are just doing crazy things, and we call this a paramagnet. This is just the definition of a system where none of the spins are aligned. Okay. So what do we have? If you imagine plotting the temperature, then at low T, we have a ferromagnet. And at high T, we have a paramagnet. And it turns out that there is a critical point in the middle called Tc. Okay? At Tc, we have what's called a phase transition between the ferromagnet and the paramagnet. Okay? The goal of today is to understand carefully what happens at this phase transition point using quantum field theory. So we will use quantum field theory to understand this point. Okay? That is the goal of today. Okay. Any questions about this? Everyone happy so far? There's one question. Yeah, okay. See. Yeah, question.
Yeah, so about that path integral you have written, is it you are taking integral over all the possible direction as well as all the sides, or you are just integrating over one side but every possible direction?
Very good. I'm on every single site. I'm integrating over all the directions.
Okay.
Okay. Yeah, the notation is a bit clunky. That's what I tried to mean with the D and I. But yeah, every site, all.
Okay.
Good question.
Yeah.
Any other questions? Okay. Okay, great. So now this is pretty simple, but the truth is it's still a little bit too complicated. You see, this Heisenberg model has a continuous degree of freedom. I want to do something even simpler. So I'm going to not talk about the Heisenberg model, although all the ideas I'm going to say actually work for that as well. We're going to now talk about a simpler model still. And that model is the 2D Ising model. In fact, I'm going to not do it only in 2D. I'm going to change the D pretty soon. But for now, it might help you to think about the 2D Ising model. It's the simplest to visualize. So what is the 2D Ising model? Again, many of you will have studied it already. Let me just remind you what it is if you've not seen it before. The 2D Ising model is very similar. It involves a lattice, okay? In this case, we're going to take a 2D lattice, just like the picture shows. And now on each lattice, we have a degree of freedom, which I'm going to call sigma. Sigma sub I lives on the sides of the lattice. But sigma sub I is now only plus or minus 1, okay? It is not a continuous degree of freedom. It's a discrete variable. It's either plus 1 or minus 1. We can still draw a picture. So for example, if it's plus 1, I'll draw an arrow pointing up. If it's minus 1, I'll draw an arrow pointing down. Okay, so for example, here we again have a picture like this of the configuration, but the spins can only point either up or down. Okay, so you can think of this as being up or down. Okay. The Hamiltonian of the 2D Ising model, you can guess it, is going to be minus j, again, sum over ij, sigma I, sigma j. Okay. So I want everyone to note, so basically, again, what this does is, at each lattice site, it looks at a link. So you sum over all the links, and on each site, you take the product of the two spins that are living on those two sites and multiply them together. It's a little bit simpler than in the Heisenberg model because it's just the product of numbers, plus 1 times plus 1, plus 1 times minus 1, and so on. Okay. So I'll note something important. This model has a Z2 global symmetry, by which I just mean this model has a Z2 global symmetry. which just means that if you take sigma and make it minus sigma on all of the sites, then the Hamiltonian does not change, right? Because there's a product of two of them. So there's a symmetry in my system, which is sigma goes to minus sigma. Okay. Now, this thing again has two phases. This model has two phases. And they're very, very similar to what we just showed. So let me show you what they are. Before we had the ferromagnet and the paramagnet, and again, we have the same sort of thing. So now at low T, we want to decrease the energy, and we decrease the energy by having this product, sigma I times sigma j, always be equal to 1, which means that you want all of the spins to be aligned. So for example, this is what you get at low T. And we again call this the ferromagnet. And now again at high T, we want to maximize the entropy. And so everything is just fluctuating like crazy. It looks like this. I don't know why I'm drawing it exactly the same on the two things. That's not what I meant to do. It's really at random here. Okay, and this is what's happening at high T. So this is again the paramagnet. Okay, so it's a lot like the picture I drew previously, except that the degrees of freedom are only plus or minus 1. Now, again, there's a phase transition between the two of them. We'll come to that in a second. But first, I want to point out something interesting. What we can do is we can compute the expectation value of the sum over all the spins, the average expectation value of all the spins. Okay, I'm just going to call it sigma I. It doesn't depend on the value of I. And what is that? Well, you see, in this phase, on the phase that we see over here, all the spins are aligned. So we're going to end up getting some value of this m, this sigma I, which is not equal to 0. This expectation value is called the magnetization. Okay. And on the left-hand side, in the ferromagnetic phase, this is not 0. Note that this object changes under the global symmetry. If I take sigma to minus sigma, I get m goes to minus m. So what that means is the Z2 symmetry is what we call spontaneously broken. I just mean that there is a vacuum expectation value for this sigma, which is non-zero. Because m goes to minus m, this spontaneously breaks the Z2 symmetry. On the other hand, in the high temperature phase, if you try to take the average value of this sigma, you get plus 1 here, minus 1 here, plus, minus, minus, plus, blah, 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 blah. It all averages out and gives you 0. Okay. So over here, there is no net magnetization, and we say the Z2 symmetry is unbroken. Okay. And again, there's a phase transition at this point, Tc, between these two phases. Now, I can show you something a little bit more quantitative maybe, which is that you can imagine making a plot. Okay, so I'm going to make a plot of this expectation value of sigma as a function of temperature. At very low temperature, this thing is non-zero. You get some sort of non-zero value, but it goes to 0 at Tc, and then it's strictly 0 everywhere else. Okay. So for an infinite system, the plot, okay, it doesn't look like that because I did a terrible picture. 1 second. Should do this a bit better. Okay, that's still horrible, but you get the idea. It goes down, and importantly, it just goes down. Oh man, it goes down and it stops like this. Okay, at Tc. So notice there's something interesting happening here. There is a non-analyticity in sigma. There's a kink in sigma here. It's not smooth. Again, that's because there's a phase transition. There's a phase transition. So now crazy things happen at this phase transition. And I want to now show you a little picture from a simulation of this to show you what I mean by crazy things. The crazy thing that happens is that at the phase transition, fluctuations happen at all scales. Okay. So I want to show you a picture. Before I do that, let me explain what the picture means. In the picture I'm about to show you, we look at a 2D lattice. Every time sigma is +1, we color it white. And if it's -1, we color it black. Okay, that's what's happening in the picture I'm about to show you. So you'll see there'll be some sort of grid, okay, with some white squares and some black squares. All right. Okay, let's look at it. I'm going to stop sharing this. And now I'm going to start sharing. I'm going to start sharing. this. Okay. Can everyone see a YouTube video? Is that on the screen for everyone? By everyone, I really mean Rakin. Yeah, you can see it. Okay, cool. All right. This is a simulation of the 2D Ising model. Okay, let's take a look. Okay. Can people see things? Okay. So let me just pause this and talk about this. This is showing the critical Ising model. It's just a simulation at very large sizes. Okay. Critical means the temperature is exactly at TC. They have adjusted the temperature to be at the critical temperature. Okay. Now the point is there are going to be 4 pictures here. One of them is much more zoomed in than the others. Your task is to figure out which of them is zoomed in. Okay. Okay. Which of these is zoomed in? Anyone? It's kind of hard to tell, right? What this means is you see that there are fluctuations, but the fluctuations happen at all scales in such a way that it's very hard to tell which of them is zoomed in. And now let's see. Okay. Which is a zoomed in version of that. Which is a zoomed in version of that. Okay. So this is quite incredible, right? You can really see what this means. There is really no notion of scale in the 2D Ising model at the critical point. Okay, now back to the lecture. Are there any questions at this point about what we just saw?
There are a few. You want to take
sorry.
a few questions?
Okay, right, yeah, okay, very good. So let me first share my thing.
Okay.
Is this working?
So one of the questions is, I'll just paraphrase.
Please, yeah.
Yeah. So can you impose different conditions, like boundary conditions, on this 2D Ising model, like topological conditions? Can it be a toroid or a Mobius strip, or basically
totally,
taking
that's
the Ising model on a different?
Yeah, absolutely. So I mean, when you do a simulation, you specify boundary conditions. So for example, you can make it a torus, in which case we identify this with this. Okay. You can make it a Mobius strip. That's also completely fine. It's all totally fine. You can do this. Very, very interesting things happen actually when you do that at the critical point. It's something that it's extremely. It's not only you can do it, you really should do it to understand what's going on. Okay. Good.
Yeah. So there's another question. Is it called paramagnetic approximation?
I don't know. I haven't made any approximations yet. I've just sort of mumbled some words. At some point, we're going to start making approximations, and then we can talk about it. But so far, I've not actually done anything, right? I just told you this is what happens, and I didn't calculate anything. I just maybe you mean this picture. To derive this picture, actually, this picture you can derive in many different ways. I'm imagining you did a simulation to see it, actually. Yeah. So there's no approximations yet. Okay. Good. Other questions?
There's a hand raised. You want?
Okay. Yeah. Let me just take that.
So about this picture, you said that it is non-analytic at TC. So can you explain a bit over that, like why we need? I'm like why we should be wondered, like when non-analytic behavior is shown, like what it tells us about the system.
Yeah, usually when there's something non-analytic, that means something interesting is happening there, I would just say. In physics in general, that's always the case. Something non-analytic means something fun is happening, just because there's something discontinuous, something is happening. Yeah, I think that's more or less it. It's always happens at a phase transition, you get something non-analytic. That's almost the definition of phase transition, to be honest.
Okay.
Yeah. Okay. Good. Okay. So now, so what we just saw was that at the phase transition point, there are crazy fluctuations happening at all scales. I now want to sort of derive a theory. Okay. We want to derive a theory to understand those fluctuations. That's the goal. Okay. And this has been really one of the great triumphs of 20th century physics, is the story that I will very quickly tell you now. Okay, the story I'm going to tell you now, it's about phase transitions, it's about the renormalization group, it's about statistical mechanics. It's really a beautiful circle of ideas. I'm going to quickly walk you through some of these ideas now, but it's really something we still study today. At the very end, I'll tell you about some very new results in this framework. Okay. So now let's imagine we are theorists and we now want to understand that simulation that I just showed you. So it seems that the important ideas, the important things are happening. It's sort of happening at long distances, right? There's these long scale fluctuations that we want to understand. So it's sort of a fun thing to do, to try to think of a long distance theory to describe only what's happening in the extreme infrared. So here is the key idea here. The key idea in this field is to introduce what's called the order parameter. Okay, we can call it the coarse-grained order parameter. All right, and let me give you an example as to what I mean by order parameter. By order parameter, imagine, for example, let me call the order parameter phi of x. Okay, what phi of x is something like the following. I want you to sum over all of the spins that are near the point x. So just sum over all the ones that are near x. So in other words, if we have here my 2D Ising model lattice, okay, and you pick some point here, x, I want you to take the average of all the spins that are near there, like maybe these guys, all of these guys, okay, or maybe all of these guys, maybe all of these guys. You know, I'm not being careful about this. I'm just saying, imagine taking the average of them in some way. That's why near is in quotes. Here, n is the number of spins that I'm summing over. Okay. Now, why am I doing this? The point is that it's actually too hard to solve the system that we have here. When I say too hard, I mean it's too hard for me. Actually, this system was solved by Onsager exactly in 2 dimensions, but we want a general approach that works for all dimensions, all systems. So we will not solve it exactly. Instead, we will look at this object, this coarse-grained order parameter, and we will hope that this object captures the key idea of what's going on. Okay. So now that we have this phi of x, notice that phi can take on basically any value, all right? Because we're averaging some things which are plus or minus 1. It can take on basically any value it likes. It's not fixed to plus or minus 1 because the average of n things that are plus or minus 1 can basically be anything, okay, if n is large enough. And also, because we're averaging over a bunch of spins near the site x, this x is not a lattice variable. If n is very big, you can imagine that this x is basically a continuous variable. It's argument. Okay? In other words, we are studying a real valued field living on a continuous coordinate x. This is exactly what we did in this whole course, right? So here's the idea. Let's just write down an effective theory for phi. Where by effective theory, I mean I'm trying to write down a theory that captures the interesting part of the physics. Where in this case, by interesting, I mean near the phase transition. Okay. And there's an important point here now before we start writing this down, which is that, remember, this sigma had a Z2 symmetry. In other words, you could take sigma and make sigma goes to minus sigma. That was the Z2 symmetry. Notice that phi also has the same Z2 symmetry. Because phi depends on sigma linearly, phi goes to minus phi is also a transformation, a symmetry operation. Okay. So what that means is our effective theory for phi should capture that symmetry, should be invariant under that symmetry. Okay. So what is our effective theory? I'm just going to imagine that we can write it like this. I'm going to imagine that we can do some sort of functional integral over some field phi. And I'm going to imagine that it looks like the exponential of minus s, where s is some sort of action for phi that I now have to write down. Okay. So what is the action for phi? Well, the name of the game here is you just write down all the terms that you can. Okay. So for example, we can have a kinetic term for phi. We can have a mass term for phi. Now, can we have a cubic interaction term for phi? Anyone? We cannot, right? Because phi transforms under a Z2 symmetry, and this term is not invariant under the Z2 symmetry. So we cannot have this. We can, however, have a lambda phi to the 4th term, okay? And so on and so forth. Basically all even powers. Okay. Now this idea that you just make up a theory that has the right symmetries is an extremely powerful one. In this context, the theory we've just constructed is called a Landau-Ginzburg theory, okay? And what we are really getting at is constructing the Landau paradigm for symmetry breaking, right? That's what we're doing right now. Okay. Okay, so here's a theory, and my claim is that this theory somehow captures the physics near the phase transition, which should be surprising to you because, I mean, you know, we're just writing in a real scalar field. Why would it do that? But we'll see, it really does. The question you should now have is that, remember, I started with something completely different, right? I started with something like this. There's a minus j here. And then somehow I'm telling you that this captures the same physics near the phase transition. So you should ask, for example, how is m square related to, you know, to beta, related to the temperature, or to j? What is the relation between these two things? This is a very hard thing to do. It's very hard to figure this out. But we can sort of understand it near the phase transition. And the way we'll do that is to understand the two phases of this model and then compare them to the two phases of the other model. That's what we're going to do. Okay. So let us first of all imagine that m square is less than 0. This m square appearing here. You have studied things like this in the Higgs part of this course, so you're familiar with this already. You know that it's fine to make m squared less than 0. And if you do, the potential for the field, this phi field, looks like this. And then what happens is that the phi field will want to be at the bottom of this or the bottom of this. So what we'll find is that the expectation value of phi is not equal to 0 anymore. It'll take on some non-zero value, which I'll call capital M. Okay. And again, m goes to minus m under the Z2 symmetry. And therefore, this is the ferromagnet. So this is meant to describe the ferromagnetic phase. I can identify that because, again, here the symmetry is spontaneously broken. I'm just writing SSBS for short. And the whole point of the ferromagnetic phase is that the Z2 symmetry is spontaneously broken. That is what it means to be a ferromagnet. Okay, so this is the ferromagnetic phase. Now, of course, we should also imagine the other phase. Imagine that m squared is greater than 0. In that case, we have v of phi looks like this. There's just one minimum. And now we have that, that the vev of phi is at the bottom of this potential, and the vev of phi is equal to 0. And this is an unbroken symmetry phase. In other words, it is the paramagnet. Okay. So again, now we can draw a picture. All right. So I can again make a plot. Here I'm putting m square. Okay. So when m squared is less than 0, this is m squared equals to 0 is at this point here. When m squared is less than 0, I have that the vev of phi is non-zero. Again, it will approach some constant value. And then over here, it will be 0. Okay. So this is the phase diagram of this Landau-Ginzburg theory. And we see it looks just like the thing that I showed you earlier. All right. So what that means is, though we cannot really identify how m squared is connected to t and tc and so on, this point, m squared equals to 0, is where t equals to tc. So at least close to the critical point, close to m squared equals to 0, we know that m squared goes like t minus tc. Okay. There's a question, what is plotted on the y-axis on the graph? This is the expectation value of phi. It's a very small, sorry, let me write that better. This is the expectation value of the field phi, where the field phi is given by this Landau-Ginzburg action. Okay. Okay, good. All right. So now we have a sort of effective description, and my claim is that this describes what's happening close to the critical point. In other words, if we are at m squared equals to 0, in other words, if we have integral d dx partial phi squared, we have here m squared phi squared, but I'm setting this m squared equal to 0, so this term goes away. And then we have a lambda phi to the 4th, and then we have everything else, blah, 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 blah. The claim is that if this is equal to 0, then we are at the phase transition point. Okay. So now, in principle, we can just calculate stuff with this. And, I wanted to understand that plot. We can now calculate things. So, for example, what we might calculate, you might be interested in the spin-spin correlation. That spin-spin correlation is basically the correlation of 5x with 5, 0. Okay, so this correlator of phi with itself separated by some distance x is basically the spin-spin correlation. Okay, I say basically because phi isn't exactly the spin, but you should expect it to be the same at long distances, and it is. Okay, let's calculate it. So we know how to calculate this, right? Because we are now extremely powerful quantum field theorists. And now what I'm going to do is I am going to now go not from 2 dimensions, but to d space-time dimensions. Sorry, d, it's all space. This is d spatial dimensions, not 2, okay? So there's now going to be a d appearing everywhere. Okay, so this is d, all right? I'm integrating d dx. And so I'm doing integral dd. So how do we do this? Remember what we do is we invert the propagator. The propagator used to be 1 over, it's like 1 over k squared plus m squared, but m is 0. So it's just 1 over k squared. Then you take a Fourier transform to get the answer. This is the propagator. This is this correlation function, right? We've all studied this in this course. We are completely in Euclidean, so it's a little bit simpler. There's no time ordering. There's no Feynman propagator, blah, blah, blah. It's just this. Okay, this is the answer. And now what is this? So we know how to do this. This integral has no scales in it. So it must be equal to 1 over x to the some power. Oh, and by the way, I ignored this interaction for now. Okay, so notice that this answer is only correct if we ignore the interaction. Only then is this statement true. And I'm doing that because I don't know how to do the thing with the lambda. Okay, and we'll get to that in a second. But for now, I'm just ignoring that that interaction. Okay, and I see there's a question in the chat. What is the motive for taking self-interaction phi to the 4th? You see, this is a good question because I added phi to the 4th, but there's probably phi to the 6th as well, phi to the 8th, phi to the 13th, not 13, phi to the 14, all these things can be there. And yeah, why am I ignoring them? We're going to get to this, okay? We're getting to that in just 5 minutes. It's an excellent question. For now, I'm ignoring it because it's too hard, okay? But we'll get to that. Okay, so for now, ignore that. And now what is this integral? Well, there are no scales in this problem. There's only x. So the answer must therefore be a power law in x. And we see that there's an integral ddk. So by dimensional analysis, what we conclude from this is that the integral must be, and again, remember, k has inverse powers of x, right? So what that means is that this goes like the power of length to the power 1 over d minus 2. And so this answer must be 1 over x to the power d minus 2. Okay, that is the answer to this integral. And then you can do this integral properly and figure out that number. But in general in life, it's good to try to do this sort of thing first and then do the hard work of doing that integral correctly, which you can do. Okay. Okay. So what this claims is that the correlation function of 2 spins separated by a distance x goes like 1 over x to the power d minus 2. This is cool, right? Because we can check this in a simulation. So we can see if this is correct or not. This is our first attempt at actually deriving something at a phase transition point. Right. So this is important. We have a power law correlation. And by the way, I'm going to write this like this. 1 over x to the power 2 delta. Okay. Where in this case, delta is clearly d minus 2 over 2. But in general, you can write it like this, where delta is some sort of number that we observe. What I'm now going to do is make a table for you of the value of delta observed. In other words, we do the simulation, okay? We compute 5x, 5, 0 from the simulation, and then we compute the number delta observed, and then we make a table of it, okay? So at the moment, our theory prediction is that delta should be equal to d minus 2 over 2, and now we should check if it really is d minus 2 over 2 or not. Okay, now simulation, what does it tell us? Okay, so I'm going to do this for different values of d. I'm going to also just make a plot of d minus 2 over 2. That's just what it sounds like. It's nothing fancy. And then finally, I'm going to give the value of delta, which is observed in the simulation. All right. So if d is 2, d minus 2 is 0. All right. And if the theory was correct, delta observed should also be 0. All right. That's not what we get. What we get is instead 1 over 8. from the simulations. Okay, the simulations really give you 0.1249999, but the true answer is 1/8. So I'm just writing that there. Okay. If you set d equal to 3, then d minus 2/2 is 1/2. But the simulations give us 0.51823. Okay. Where it's kind of close to half, but it's not half. Okay, it's really different. Okay, the error bar is very small in this measurement. It's different from 1/2. And now let's go up one more dimension to 4 dimensions. D minus 2/2 is now 1. And the experiment now, the simulation now actually does show 1. So there's something fascinating happening here. All right. What's happening is that this works better and better as we make the dimension higher. In fact, it works correctly for d greater than or equal to 4, and it doesn't work for d less than 4. In particular, this is the physically interesting one. We have 3 spatial dimensions in our world, and so it doesn't work there. Okay. There are some questions. What happens in d equals to 1? It's been answered. Indeed, there's no phase transition in 1D. Yeah, famous result. Okay. So this is the most I can show you. Okay. So now it doesn't work. Why doesn't it work? So the basic point is, of course, that I neglected the interaction terms, right? That's why it doesn't work. Okay. So by the way, this caused the physicists of the time a huge amount of confusion. Okay, that this theory wasn't working. All right. And to resolve it, we have to really understand how to deal with interacting quantum field theory. So the point is, I neglected interaction terms. Can I do this or not? So now let's revisit these interaction terms and check whether I'm allowed to ignore them. So again, I'm going to write down this S of phi. Okay. And now we have delta phi squared plus m squared phi squared. Now you put back this lambda phi to the 4th term. Okay. There's a question in the chat. Is the interaction very strong in low dimension? That is exactly the right question to ask. Okay, so now we're going to discuss that. So the way I'm going to figure out if I can neglect it or not is through the power of dimensional analysis. Okay. Let me just remind you guys a few basic things about what's going on here. Here are some equations in physics. E equals to h bar omega equals to, let's see, mc square, and then x equals to ct. Okay, this is just some basic things in physics, formulas we all know and love. Let's remember that h bar is 1 in our world, which means that energy has the same units as 1 over as frequencies. So energy is the same units as 1 over time. Okay. C is 1, which means that energy is the same units as mass. All right. And C is 1, which means space is the same units as time. So what that means is there's really only one dimensionful thing that controls all the dimensions. There's just one number. Something can only have a single number characterizing its dimension. And so, for example, we can just ask, what is the mass dimension What is the mass dimension of all quantities? We can just ask that. Okay, and that will be a number. So for example, obviously the mass dimension of mass is 1. Okay, let's look at some other things. So remember, we are taking the exponential of minus e to the minus s. That means that the dimension of the action must be equal to 0. All right. The dimension of x, from here we see dimension of distance is the same as time, which is 1 over mass, because these are the same. And so there we have the dimension of this is -1. Okay. Now, because S has an integral d dx, that means that the dimension of everything that appears here must be d, so that it can be canceled out by the minus d coming from here to give me 0 on the other side. So the dimension of delta phi squared equals to d. Okay. which means that the dimension of phi, if you trace through that, is equal to d minus 2 over 2. This is the dimension of the real scalar field. And I'm not sure if this was done in the lecture program, but this is just a basic thing to do. It was in the lecture program. Okay, done. And now you're seeing it again. Okay. Now, let's now ask, what is the dimension of lambda? The coupling. Okay. This whole thing must have dimension d. And so if you trace through what that means the dimension of lambda is equal to d minus 2 times d minus 2, which is equal to 4 minus d. So notice something interesting is happening precisely at this critical value when d equals to 4. At d equals to 4, the value of lambda, the dimension of lambda, changes sign. Okay. And that suggests that this is the right thing to think about to understand what's going on in our experiments. And so what does it mean for this thing to change sign? If we imagine computing the correlation function of phi of x, phi of 0, where now we include doing a Taylor expansion in powers of lambda. So imagine doing Feynman diagrams, there's loops or whatever, do all that stuff, okay? Try to calculate how the value of this thing changes as you add lambda. What's going to happen? Well, I'm going to expand my answer in powers of lambda. So the leading order answer is just this. Next, I can imagine including the term at order lambda, but there are no other scales in the problem. And this thing must be dimensionless, which means we must have a power of x here, and that power of x must go like 4 minus d, so that the whole thing is dimensionless. There's no other way for this to happen. Similarly, the term that is of order lambda square must come with a power of x to the 4 minus d squared, so on. So now this form is fixed by dimensional analysis. Okay, so I don't know these numbers, but this is the idea. This is fixed by dimensional analysis. And now let's look at what happens as we go through d. If d is bigger than 4, then this thing goes like 1 over x to the power d minus 4, this correction term. And this thing goes to 0 as x goes to infinity. In other words, the interaction is not important at long distances. So as long as we ask about long distance questions, we are okay it's okay for us to ignore the interaction. In the lingo, we say this is an irrelevant interaction in the renormalization group. The renormalization group is the correct way to think about this idea. On the other hand, we now see the flip side. If d is less than 4, which of course is the interesting case, then we have lambda x to the 4 minus d. And as x goes to infinity, this term also blows up. So it is very important at long distances. And this, in the lingo, is a relevant term. Okay. So indeed, someone asked us in the chat, is the interaction important in low dimensions? Yes. Okay. This interaction is important at low dimensions. And that is why we got the wrong answer when we started earlier. Okay, it's good progress. It's always good to know why you messed up. But say we actually want to solve this now. Okay, so now we want to solve the problem. So what do we do? In 2 dimensions, Onsager solved the problem exactly, has exactly solved the 2D Ising model. Okay. In all higher dimensions, it does not seem like that is possible. In particular, in 3D, for the 3D Ising model, there is no exact solution. Okay. Many people have tried to solve this, and there is no exact solution. I think if you could write down an exact solution to the 3D Ising model, that would be an amazing thing, right? I'm not sure it's possible, but many people have tried. Okay. The reason is really basically this, that it's an intrinsically strongly interacting problem, and there is no simple way to deal with it. Okay. It's perplexing because this is, of course, exactly the physically relevant case. This is the one that's important for real life. Okay. So now, in the last 1 minute, I'm just going to tell you what people are doing to solve this now. This is a topic of current research. Okay. And what people do is basically they use the idea of conformal symmetry. All right. So what I have told you is that at the critical point, there is a scale invariance. In other words, if you make the system bigger, nothing changes. It turns out there's actually a fancier invariance as well. At the critical point, you can actually change the system in a much more dramatic thing. Don't just scale the system. You can like mutilate the system completely, provided you preserve all of the angles between lines. Okay. It turns out the system is also invariant under this, and this is called a conformal transformation. Okay. And there's a lot of current research going into using the technology of these conformal transformations to understand phase transition points. This is called the conformal bootstrap. And this is the most accurate way to understand the Ising model. I said there's no exact solution, but for example, if you want to, what you can do is you can use this fancy conformal technology to make plots of what is possible. So for example, this delta is the value of delta for the spin operator that I told you about. You can imagine taking the delta for that as well as a different delta for the Hamiltonian and trying to figure out what can and cannot happen using this conformal symmetry. And very fancy techniques can show you that, for example, there's only a very small window of allowable dimensions that's allowed. Okay? Everything outside of this is not possible. And of course, the middle of this is exactly the value that we think is correct. 0.518, blah, 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 blah. And again, this has some other value which we think is correct from simulations. So even though there's no exact solution, people have really almost completely solved this particular thing using the conformal bootstrap. And more importantly, there's just a lot of beautiful structure that you can use in the idea of conformal field theory, or CFT, to understand not just phase transitions, but really many different things in theoretical physics. Okay. Okay. So we are out of time, so I'm going to stop now. I just feel a bit bad because I told you about boiling water, and I didn't say anything about boiling water. I'm going to tell you about boiling water, and I'm going to stop. If you look at the phase diagram of boiling water, the phase diagram of water looks like this. Yeah.
You can take a bit more time because you started, I think, 7-8 minutes left.
Yeah, it's okay. I sort of do want to end on time, so I'll just say this very quickly. If you look at the phase diagram of water, okay, then you can make a plot of pressure versus temperature, and the phase diagram looks something like this. Try to get this right. Then okay, it's something like liquid, gas, and solid. Okay, this is the famous triple point, which is 0 degrees Celsius. All right, and now sorry, this line actually goes on forever. I don't know what it does, but this line ends. Okay. In other words, there's a transition between liquid and gas. This is the one that everyone knows when you boil water to make your tea or whatever. You are progressing through this transition line. But if you increase this high enough at some temperature, whose number I have unfortunately forgotten, then this phase transition line actually ends at what's called a critical point. This critical point is exactly the 3D Ising critical point. Okay? It's exactly the same one as the one I showed you earlier. And you can convince yourself why that is. It has to do with the fact that if you start writing down terms like this one here, then the truth is this is the most general action near any critical point. But in water, there is no Z2 symmetry, but you can add a term. So you can imagine adding a term like this. However, as you change the pressure and the temperature, this phi cube term will at some point go away. And when it does, then you get exactly the Ising theory. And this going away is, in fact, exactly this point here. So the critical point of water is exactly the 3D ising critical point. Okay. So now I have satisfied my the thing I promised to tell you about boiling water. But the overall upshot of all of this is really just that many systems are described by quantum field theory. Again, the idea here is that there is some notion of locality, because we had spins that were interacting by a short-range interaction, and then some notion of fluctuations, which in this case happened because of statistical mechanics, or thermal fluctuations, statistical/thermal. And these two ideas, when you combine them together, really can be well described by the framework of quantum field theory. Okay, and that's all that I wanted to tell you. I'm happy to give you references on this. This topic is still unfolding now, and the bootstrap is an area of very active research that many people are working on. Okay, thank you, everyone.
Okay.
That ends my lecture. Questions?
Thank you.